Now, even though we've recommended SMA, sometimes that's not always practical for people, especially companies that are making host application processors. To have SMA connectors for every single interface that's on a host application processor can be very difficult. They simply just take up too much room. And so it's okay for people to use other things. I've got a couple here, SMP, MMBX, MMCX. These are all signal integrity quality connectors. They're fine to use for connectivity to your MIPI product, because for all of these, it's very easy to find pigtails or adapter cables that go to SMA. So even if you brought a product like this to an interop event, if you had the proper pigtails, you could then connect to a product that had SMA. So there's lots of different types of SMA adapters are available. The point is to look for something that can be easily adapted to SMA and that'll meet any signal integrity requirements that you need for doing the phi measurements. And all of these do. That's what they're designed for. Now, with respect to MPhi, for today, we're thinking that all of these signal integrity quality connectors are going to be okay for using in MPhi 2. We're looking at using SMP in some of our test fixtures, just because it's a little bit smaller, it takes up a little less room. LLI is a little bit of a special case that we're still trying to solve. If you've gone through the LLI specification, you realize that it has some tight skew requirements. And this is something that the work group is still talking about and trying to figure out what's going to be the best recommendation for this. But when you're looking ahead to MPhi, I'm not saying that not to use SMA or not to use this, but just keep in mind that you want to use something that meets any kind of signal integrity requirements for doing, especially for doing phi measurements. Regarding BIF, this is one of the other work groups I mentioned. We've worked with them to help them define some connectivity. If you're familiar with BIF, it's a relatively, well, it is low speed. And so a lot of those signal integrity issues that you need to pay attention to when picking a connector doesn't apply as much in BIF. So what we've got here, this is another board that we designed for BIF. And essentially what it is, it allows you to connect power, ground, and signal to any BIF slave and BIF host and connect them together, and then connect to BIF slaves. The connectors are essentially 3-pin 100 mil headers, very commonly used and very inexpensive. So, but this is something that really anybody who's implementing BIF can look at this and then design their part with a connector that will be able to connect to this relatively easily. Any questions on connectivity before we move on? Like I said, some of the issues regarding connectivity, particularly around MPhi, haven't been answered yet, but that's something that's still ongoing. And we have a recommendation. I'm sure we'll make sure as many people, anybody that needs to find out will find out about it. All right, next is, question?
Just wondering, those connectors, are those also on the test website, or are they also the, say, reference, list of reference connectors? Are they on the test website, or are they, which part of the website are they?
Yeah, if you go back, these, well, like this one in particular, it's on the testing website. We went back to these reference schematics are also on the testing website, so you can find that information there.
Oh, thank you.
Yeah. Any other questions about connectivity? All right, I'm going to go into test modes and test enablement. So of course, test modes are a mode that you put your device in to allow it to be tested or make it easier to test. Test enablement isn't necessarily about a specific mode that the device has, but maybe some actions or some functions that your product can do, or you need to be ready to enable your product to do, that are within the scope of the specification, that'll make testing a little bit easier. You'll see what I mean as we get into some more detail here. I'm going to talk about the test modes and test enablement for DSI, CSI, DPhi, and then also looking ahead a little bit to UniPro and LOI. So first off, in DSI, if you've looked at the CTS for DSI, there's well over 100 test cases in that. And so one of the things that we've done is to create a test preparation form that narrows down what exactly we need to do in order to perform all of those test cases. Because some of them, there's going to be an amount of redundancy. For example, if a device supports EOTP or doesn't support EOTP, if a device supports continuous clocking or non-continuous clocking, those are different options that people may implement. The test preparation form helps us figure out which test cases do we actually need to perform and observe in order to say that we've met the requirements in the CTS. So there may be some configurations that we'll do that will actually show us that we passed the requirements for 4 or 5 items in the CTS. So that's the point of the test preparation form, is to help us kind of consolidate and do the testing faster. Regarding test enablement for DSI, you need to be able to put your device into ULPS mode, either to create the entry and exit sequence or be prepared to receive the entry and exit sequences. You have to prepare and document the proper video timing. So this is something that some panels can be very sensitive to. And when we're testing them, if we don't know the proper video timing, that can make the test time drag out a great deal. So properly documenting the video timing is an important part of enabling testing for DSI peripherals. And then also the initialization sequence. So a lot of, especially command mode peripherals, it seems to be more often, will have a very specific sequence of DSI and DCS commands in order to enable them and turn them on. In order for it to be tested, either at an IoT event, in a lab, with one of your partners, you need to document that initialization sequence very well and specify exactly which commands need to be sent for all of the modes that peripheral supports. So a peripheral may support different number of lanes, different image formats, different data rates, and to enable those different configurations, you may have a different initialization sequence. To make testing easier in any venue, it's important to document all of these things. So that's part of test enablement. Questions on DSI test enablement? All right. A CSI2, similarly, there's a lot of test cases, and some of them have some overlap. So again, we've created a test preparation form to help you see exactly which configurations you need to configure your device to be able to do which functions you need to demonstrate in order to perform those tests. Again, ULPS entry and exit is an important one. Video timing on the receiver side and on the transmitter side, the receiver needs to know the timing coming out of the sensor in order to be able to properly capture and display an image. And on the sensor side, I've highlighted this one. You must be able to provide the proper software and hardware to control a sensor. If you go into the CSI2 specification, the CSI2 transmitter is controlled or programmed over the CCI or I2C bus. When we've done the testing for CSI2 devices, either in the lab or at an IoT event, we haven't tested the I2C configuration because every single sensor is going to have a different command set and a different setup that is non-trivial to produce in a short period of time. So what we've done is asked the CSI2 sensor providers to provide the necessary hardware and software to control that sensor from a PC. So for example, the evaluation board that a sensor is on may also have a USB interface that you can connect to a PC, and then they have their own software for controlling the camera, and that's something they might use for doing demonstrations, something they might provide to their partners. That's the software that we need in order to enable proper testing of the CSI2 transmitter. Any questions on that regarding to test enablement for CSI2? All right. For DeFi, typically when we're testing a DeFi, it's a PHY layer under either CSI2 or DSI protocol. So everything that we had to do for CSI2, everything we had to do for DSI, we have to also be ready to do that, even if we're just testing the DeFi layer of that product. It's best if we can configure the product to source the DeFi reference test pattern. If you look into the DeFi test suite, it describes the DeFi reference test pattern. Essentially what it is we designed it to be an image, since the common application is either a display or a camera. It's both dealing with imaging. It looks like a color bar, a grayscale color bar, but each of the bars is a pattern of varying transition density. So we'll have one bar that's 10, 10, 10. We'll have another bar that's 00, 11, 00. Another bar that's 0, 0, 0, 1, 1, 1, 0, 0, 0. We'll also have a bar in there that's a lone bit pattern, so a string of zeros followed by a 1, followed by a string of zeros. The point of that reference test pattern is to stress the transmitter and receiver, giving them a pattern that's relatively difficult to handle. So if you're able to do that, if you're able to source that reference test pattern, then in the transmissions from your device, you'll actually have all of the patterns that are necessary for performing a DeFi conformance testing. So again, that pattern is described in the DeFi conformance test suite. We also have a test little tool widget that's available for producing that test pattern as an image of different sizes, so that if you can configure your product to send a particular image, this test tool can help you produce that image. One other thing that's necessary for DeFi S-parameter testing is to, especially on the receiver side, be able to force the high-speed termination on so that we can perform the S-parameter measurement on that. Because if you think of it, in normal operation, even when you're sending an image to a DeFi receiver, its high-speed termination is turning on and off as it's receiving HS bursts and then going back into LP mode. In order to properly perform the S-parameter measurements, we need a mode where the HS high-speed termination will always be on. So that's something to pay attention to for DeFi test enablement. Question regarding DeFi test enablement? All right. Unipro has actually put together you could call it a requirements document for their interop workshops, what you need to do to a device in order to have all the proper test functions for doing interoperability testing in Unipro. They've documented that here, and I've provided the link for it. So if you're interested in test enablement for Unipro, this would be the document to look at. Now, the next couple slides are a little bit more forward-looking as far as the test modes that Unipro and LLI have implemented to enable testing. So you might recall, kind of one of the missions of Test Investigation Group was to help work groups include design for test, include test modes in their specification, such that after it's been implemented, we still have some test functions built in there. And Unipro and LLI were really kind of the first work groups that we were really able to work with and put in some test modes. So what we've done is in Unipro and LLI, they built in test modes to enable M5 testing, to exercise the phi through the Unipro or LLI layer. Now, the way they work is similar in structure. Essentially, you send a packet, a protocol packet, it's a compliant protocol packet, to a device, and that's going to put it into a test mode. Now the packets are different depending on whether it's Unipro or LLI, but the principle is the same. And those packets were designed such that they can be sourced from a Unipro device, an LLI device, or they're simple enough that you could even use a pattern generator to create them. And essentially what they do is they'll put the receiving device into a pattern checking mode, and the transmitting device will start to send a pattern. And that pattern is known to the receiving device, and it's just going to check to see if it's receiving that pattern correctly, and then it'll log any errors. When the pattern's done, the transmitting device will send another packet to the receiver to report back if any errors were received. And so by doing that, you've kind of created your own little BER interoperability test. You know how much data you sent, you know if any errors were detected, and you can actually do a BER measurement from that. I've got a little diagram to show how this is done. So first, your test equipment, your MIPI generator will start sending a pattern to the receiver.